Hello, my name is Kevin Davis, and this is my Lab 1 report for constant velocity. To introduce, the purpose of the lab is to compare the position of a rolling object at constant velocity, experimentally using the tracker application, and then computationally using GlowScript. The object that I chose was a white wiffle ball. Now, Newton's second law, the momentum principle, states that F net equals delta P, which is the change in position, divided by delta t, which is the change in time. Manipulating this formula, we can also get the position update formula. P sub f, or final position, equals P sub I, initial position, plus F net times delta t, or the change in time. Manipulating the position update, we can get the velocity update formula, as shown at the bottom, which is final velocity, or v sub f, equals initial velocity, v sub I, plus F net divided by m, the mass of the object, times delta t, or the change in time. The procedure of this lab is pretty simple. The first step is to capture video of any object rolling at a constant speed in a straight line. Then you import the video, the second step, to Tracker to track the position of the point mass frame by frame in the application manually. Then you use step 3, the GlowScript starter code in the Lab 1 resources, and your data from Tracker to create a computational model of the same ball rolling in the same conditions, however, without friction or air resistance. Then the fourth step is to plot both of the sets of data generated by Tracker and GlowScript, respectively, and compare the outcomes of the experimental and the computational data. My experimental data is as shown. The position time graph in the middle of the screen is a relatively straight line, which adds up for constant velocity. And then in the video, it shows a white wiffle ball rolling, and each little diamond here is a position and a time shown in the table. An analysis of this, to analyze the data, you take any two positions. I chose the very first time and the second time. You find the initial and the final position, which is just the furthered, not time, but displacement, not displacement, position. And you turn them into vectors, as shown. Then, to calculate the average velocity for GlowScript, and the average velocity just in general of the object, you take displacement over the change in time, or the final position minus the initial position over the change in time to get the average velocity. And the average velocity of my white wiffle ball was 0.712 meters per second. Now, to get this data and then to get the computational analysis to work, you take the initial position and put it into the ball's initial position, and then the ball's velocity you turn into the average velocity from your experimental data. You also change delta t into 1 divided by 30, which corresponds to the 30 frames per second frame rate of the camera recording it. Then, to find the ball's velocity and position at each given time, you need to implement the velocity and position update formula that we calculated from Newton's second law into the code, as shown below. Here's a visual comparison of the data between the computational and experimental, aka GlowScript and Tracker. As you see, the Tracker slope is a little bit less steep and isn't completely a straight line, whereas the GlowScript is straight and a little bit steeper of a slope. Now, why are there deviations? Well, first off, there may be human error when recording the video. Because I was close, there may have been lens distortion, which changes the speed of the object due to the lenses changing the ball's position. Additionally, when tracking it, the position or the time may have been wrong due to human error. Rounding may have also changed the calculations of my values. And then outside forces like friction or air resistance may have affected the calculations. Now, 2 what ifs are asked. First off, what if the minus x and positive x were interchanged? If they were interchanged, the slopes would be negative on the graph. However, the magnitudes of the values would be the same. The other what if asked is the net force 0? Hypothetically, it is. However, forces like friction or air resistance play a part in it, which make the net force not zero.